So today we are going to consider problems on topic Euler circuit, and maybe we can consider one more task later. One second. Так. Where is this task? Okay, you have a airport GFK. You must to visit all the airports uh, through all the use all the dictionaries. So how do we do it? How else we do it? And I remind you what is Euler tool. Euler tool. Where's Euler tool? Так. So Euler trail or Euler tour or Euler circuit in undirected graph is open walk that use each edge exactly once. So we in the previous lecture we consider some algorithm that finds Euler circuit, and obviously in this task we must to apply this algorithm, but how do we do it? Okay, who can suggest a native natural decision solution of this task? If we use Euler circuit algorithm. Just the most stupid solution. Usually it means полный перебор. How do we сейчас how can we consider all cases? When we try to use этот Euler circuit algorithm. Do you understand Euler circuit algorithm or not? Okay. The most native solution is greedy solution, and when we try to when we try it in our DFS, in our algorithm, enter to the vertical with smallest vertical order. But and this native solution is correct. But why? This native solution is the most effective solution, greedy solution, and but why is it true? But why is greedy algorithm that I suggested is true, is correct? Because in our stack, in our what we consider vector or stack or deck, we consider okay, we consider stack and we consider result. In our stack, we create edges. We put always we put edge with smallest lexical order, and in our result we have to put the edges when we have reached some point, some vertex with no edges, with no unused edges. Okay, in one good example, we have some this graph, some graph. Here's the vertices with smallest lexical order. Пусть он будет унаправлен. And we, in the first iteration, we go to 2 verticals and 3. Then we go to 1 vertical, 1 vertex. Then we go to 1 vertex, and we get that we have no edges here, unused edges. So we pop from our stack edges while we reach edge with vertices, with some edges that we didn't use. So when we do it, we put this vertex to stack, so this edge to stack. So why is answer will be right? Why is answer will be right? Why? Okay. We just when we confused about cases, when we confused about the answer, we must consider cases. What cases will be? We consider some last vertical, some last vertex, and current vertex, and we and somehow we we visited vertex C, that there is no edge, there is no, we consider all the edges of C, there is no edges, so we must to pop from our stacks all the vertices while until we meet vertex with some edges. So there's a vertex. Let's consider that this edge, this walk begins from less smaller lexical order than this edge, this walk. So we must visit this vertex, then we return and must visit this way. So this walk. So there's one case when statement we must to prove that CL walk, just CL is what is last walk. No, in the correct answer. So what cases will be? Case one. Case one. That's good, but because we when a walk doesn't intersect LC walk, answer will be CL, then just CL AL, just AL plus AL. No, reversed answer. I mean. That's okay. LC is the last. LC is the last walk. LC. We push CL and plus AL and reverse the answer. No, or we just push front all the vertices. In this case, do you remember? We consider that way. Сейчас где это было? We considered that we must to reverse result, and that is true. And that's this case is key. This case. Second case, when we intersect LA walk, LC walk with a LA walk. We have LA walk. LA walk must be closed walk. No, I think. No, да, LA walk must be closed walk, but you consider in this case. But I think you understand me. So we consider the case when LA walk intersect LC walk. LC walk and ends, and suppose it ends and LC and with somewhere in LC walk. and but in this case we have to have to just LC walk is the first, then we visit LA walk. That means we we visit LA walk, then we visit LC walk. So if we visit LA walk, we have to enter to LC, then we return from LC, then we return from this. When we return from this, and we push CA, then we return to this vertical and push LA, L. Then we return. Then we return. We push LA, AL, and then we push just CA, AL, and then AL. Then we have two ALs. Okay, I think you understand that we push this walk at the end. So this case is true too. Last case when we when we visit our vertical or our vertex, when we visit some vertex and continue go, we consider this case. So we push LA, we enter LA, and we visit C again. Then we так, тут возникает сейчас. There is contradiction because if we visit LA, then we have to visit AC, then we return, and сейчас Сейчас, подождите. Нет, no. There is no contradiction. We visit VL, and this H is used, so the answer will be CA and AL. This walk is used already. So we consider all the cases. We prove that LC is last walk. It means that if we consider some graph, in this graph we when we start a walk, when we start algorithm, in every vertex, every time we in every vertex we in our stack we push last we push edges with highest lexical with higher lexical order. That means we get some order. If we reverse it, we get smallest lexical order. Okay. Do you have questions? Надо было написать. Let's see this last walk. LA walk with basic smallest with the smallest lexical order. Так, ладно. Do you have questions? The most difficult in this task is consider cases. LA these cases. You must in really hard task you must concentrate only on abstract cases, I think. Most you have to write describe cases most correctly. Точнее, сейчас describe cases как most simple way. So let's solve this task using let's solve this task. Let's code this task. Так. maybe you don't understand cases, why we consider these cases. Ask questions if you don't understand. So in this task, let's consider as we must to consider the edge with smallest vertical order. Let's and notice that it's not just a graph, it's multigraph, because there's no constraints on edges. I mean edges, the same edges. We have the same edges. We can have the same edges in graphs. So to store these edges, we are going to use multiset. Did you remember what is multiset? Do you remember? In multiset is based on red-black tree or AVL tree, and it can contain что это такое? It can contain similar vertices, similar case. So we contain our edges in multiset, and we have to this will be our graph. So for every edge we contain the vertex with edge. So we use vector, but we want to use vector vectors, but in this case we want to we want to get vertex. We want to get edges using string, and this will be not vector, just vector. We use unordered map. Unordered map of multisets, and we want to get this multiset by string. So we have to initialize our data structure. If we iterate through this map, we have to we get pairs, and we just get pairs of tickets. And ticket, not tickets. And we get no, I mean tickets, ticket. And we contain ticket 2, ticket 1 in every. We consider, we initialize our map. In multi-map, in multi-map, there is no methods like just assign. We must insert tickets, insert edges. Так, min vertices. So the next is our Euler circuit algorithm. We prove that when we choose if we choose greedy strategy and we every time we consider H with smallest lexical order, it will be worked. So in deck we contain our result. In deck in stack we contain H's. So once again we что написал result. Instead we contain давайте я напишу нормально. States. Окей. Так. Где? You can look in mirror board, and result will be just this array. And stack will be this array. I have already denoted like S, like edges. Okay, edges. Not states, edges. Так. Ну, не совсем edges, конечно, in this case. Ладно. Let it be states in this example. So we in place in our stack the first vertical JFK, the first vertex, and let's consider the phase with stack implementation while stack is not empty. Our stack just push something. We push we get another vertex from our stack, then we consider edge with smallest lexical order. By the way, in C++, when you there's for strings there's default comparator. that in this comparator implemented as just lexical just if you sort vector of strings, you get lexicographic lexica just smallest lexical order. Называется. Yes, smallest lexical order. So after that we erase as we consider this edge. Just erase it. In previous implementation in the lecture I told that we contain pointers on edges. In this implementation we just erase edges and we get another edge. So we just in place next or next vertex. But if you consider, just let's see, 1 second. Blin. I have streamer mode again and I didn't see your questions. I open chat. You didn't write questions. So we consider in mirror desk we just implement that we go through our edge in lexical smallest lexical order, and we have cycle here, and we have to pop from our cycle vertices until we reach vertex with no edges. So let's notice that this step makes we have to make before we want to go in the next edge, in the next vertex. So we consider until we don't meet edge with no vertices, it means ms top until ms top not empty. Until ms top is empty. There is no vertices. There's no edges. We just in place to result, in place front in our deck result is a stop. Then we as pop, and that's all I think. That's all the algorithm. Very short. So after you finish your algorithm in interview, you must to check that all algorithm is correct. So let me read again description. Okay. Okay, constraints. Let's consider constraints. Okay. Okay, that's fine. So consider algorithm. We initialize our map, our unrotated map with edges. Then we create resultant states. States that in this states we just contain just implement DFS based on states, based on stack. We can implement DFS, recursion DFS, and based on stack. We implement it on stack. Okay, I see. The mistake. So okay, after that we just push first vertex, then we if there's an edge, we just push it. We just pop and push it, or we pop our vertices from stack, or our not ver no this in this example is edge. We contain vertices vertices. So well, that's okay. That's okay too. So we just pop vertices and we push vertices in place front. I noticed that I forgot about return vector string, I think, of what as we replace front, our result gets right order. And last time we consider some case. We try to compile with our eyes. Okay, let's consider this case. Okay, GFK as ATL, GFK ATL, GFK. Then we push SVO, ATL, SVO. Then we pop. Then we enter into the cycle, and we get that there is a mistake, because when we pop and in place all our vertices, we just get that. There's no edge and there's must be one more empty. Let's learn what to return, just the same. Okay. You can ask questions, I see it now. JFK. Блин, it's not states, just as. Ну, черт. Окей. Accepted. Так, once again. Вообще, in general, you should to check your code again and again. This skill is very useful, independent on your level. You can often get bored from this, but на самом деле it economes a lot of time. Let's submit this, and this is very useful. Oh, okay, this is very useful for interviews. Мы что-то долго. Окей. Так. Why is it not? We can. It's okay. That's not bad, but. Блин, что за фигня? Okay. That's not bad, but we can do it better, I think. No, what can we do? By the way, no, use in place for non-primitive types. In primitive types, use push, because copy of smaller bytes is of smaller count of bytes is ну сейчас сейчас you create copy of primitive types, and it's faster than just contain pointer to structure. To the primitive type, to the variable. So in primitive types, use push instead of in place. What can I can I improve it? No, you can give me a hint where I can improve it. It's not necessary, but it's not necessary. So submit another time, and ага. Ну, 86. Ну, как бы. Окей, there is it's already optimal of solution, because we can get different time when we launch it. So okay, let's consider another task. Do you know what is De Bruijn graph? Do you have discrete analysis? De Bruijn graph. De Bruijn. It's called De Bruijn. Okay. De Bruijn. This task we Okay, we consider another task on Euler circuit. I try to do it faster. There is a safe protected password. The password is a sequence of n digit. So давайте let's consider De Bruijn. Так, what is De Bruijn graph? Давайте read this task. So okay, we must to iterate through all the sequences, and it will be n to the power of k sequences, n to the power of k. We have n digits, we have k range, and here we have n digits. So we have to iterate through k, so we have to get k to the power of n sequences, different sequences. And we have a safe, and in this safe we just do a iteration through all the sequences. And how to do it fast, how to do it with a smaller count of iterations. We can consider graph De Bruijn graph. This formal definition, we have some alphabet, and we have vertices. Notice that we have n minus тут не написано n minus 1 vertices in every set. I mean n minus m minus 1 minus 1 letters. What's the idea? We try to do iteration, and we try to iterate through all this n to the power of k sequences, and we just consider a graph with n to the power of k minus 1 vertices, and try to do a step in every vertical. If the prefix of vertical is the suffix of vertical that we income, for example, in this way, null one is equals to prefix of some vertical null one, for example. We just create edge between them, and null one equals to null one in this vertex prefix, for example. Very simple, I think. And we try to do a step. So if you notice that if we do Euler's, if we find Euler circuit in this graph, for example, we can find our sequence, our smaller sequence, because we iterate through all the vertices, and we get all combinations of our sequence n to the power of k. To understand the idea of Euler cycle, of apply Euler cycle und Graph de Bruijn. I try to do it faster, because we have no time. You can read formal. You can read this definition again, these properties. To understand more correctly. Okay. So we try to code this. Let we must get, if we have n verticals and n digits and k range, we have to create graph with how many vertices, but never code like this. Never code like this. I require that you have to write beautiful code. This is not beautiful. This is just fast way. So Right. So you consider some graph, and how many vertices once again will be in this graph. 2 to the power of k minus 1. Okay. Let's initialize edges of this graph. Um, we from буду это комментировать null to the g size. Iterate through all this also all vertices and try to create edge. Try to create edge between we can iterate through all the vertices and create edges, but notice that how to get another vertices, another vertex, another edge if we locate it in some vertex. We just consider some suffix n minus 1 n minus 1. This will be just null 1 and add all digits in the sequence. Null 1 null must be this edge, and null 1 null 1 1 this edge. That's all. Yeah? This is also algorithm of how we create edges. We just try to suffix. Нет, it will be just 61 t suffix p suffix 2 null suffix 2 less than what? Less than n, because we have only n digits. In this example we have 2 digits, null and 1. Suffix 2 less than n. So just in this graph we just push, we consider from vertex, and we just push back, not in place, because we have primitive types. Push what? By the way, why are we consider numbers? Why don't we consider vertices? I mean strings, because we can represent every string of digits as just a decimal or some number. We can there's a formula how to represent numbers. into the chemical system, decimal system, we just we have some vertex, and we try to cut нет. We try to cut the first number in this. How to do it? By the way, how to do it? Cut the first number digit of I mean how to find the suffix of this number that contains n-1 k-1 digits. Блин, ну сейчас как вот, я не знаю. It's some number system. Не знаю. Вот, here we have some formula, and so have to I don't know how to do it in English. Ладно, consider how to do it in numbers. So блин, сейчас, секунду. Так, вот, for example, we have a hexadecimal system, and how to find 8 digit in this system? We just notice that we just divide this number by 16, and we get нет, we divide our number by 16 to the power of 2 and get 16 to the power of 3 and get just 8 if we divide нацело. Okay, and how to find first number? We just we just get model by 16 and get this number. So we divided by what? By n to the power of k minus 2 or not. I can do a mistake in this place. N to the power of так. No, we want to get not the first number, we want to get these numbers. It means we just divide our number by 16 in this example, and we get prefix, suffix, suffix of this number. So, and then we just create edge between suffix 2. So that's all. Then we just code the algorithm, and that's all. Let it be let it be DFS, usual DFS. Let DFS that's in this we just call DFS from null vertex, and in result we have to push the first chess. In result we have to push what? Так, ну-ка, окей, in result we have to push nothing, and don't forget about how to output our string. So here for int 4 we just do the simple output and return str. So how to we okay just it can be we just do this result global. I try to do it fast. Я уже вызвал. Так, and so how can we implement Euler circuit algorithm in recursive way? Так. Тут so if there is no edge, давайте, ладно, тут тоже вынесем. Ой. If there is no edge, я запутался сам. Ой-ой-ой. Ага. Да ё-моё. Так, if there is no edges, we just while we just return ага, я вынес. If there is no edges, gv, if gv is empty, we just return from our DFS and push to result, push front. This vertex, да? This vertex. And and we just push it. And we just call DFS from color from next edge. Okay, you have to go. No, you just do you require to have do you need to have to go or not? I stuck. Okay, in a way return from it. There's no next var. Okay, in this way we get much more simpler more simpler algorithm. No, well, okay, of course we do next plus and ага, что я сделал? Okay, there is another visited, not visited. Do we need not visited or not? Not GV. What is GV? Stack. We contain stack. Okay. In previous solution we contain three stacks. Нет, we can't. Okay. Okay, all the variable will be again. Okay, will be global. Do you get the idea? I can't promise that it will be fast. Что мы делаем? We push to our stack. Так, we check. Then we push then we push to our stack new vertex. Ничего сделал. Okay, current get, then we okay, we have already current node. Okay, I sent you code a little bit later. We have to put not where, not just numbers. We have to put last. We have to put only one digit to get sequence. Okay, that's not a good idea. Solve hard task for 15 minutes. So you don't have to go. I will send you code and I comment it, so you can free to go.